So, heat transfer, okay? This is all about quantifying the way, the rate, and sort of the what, the how much, and the how fast of energy moving around between materials, okay, between objects and their surroundings, between surroundings and objects, as a result of temperature gradients. Okay, so we've all at least heard of the concept of conduction, of convection, and of radiation. And that's those three things are going to be like the focus of this class. And heat transfer, so thermo, which you have all taken at this point, was all about the how much, right? Some fluid has a particular state going into a system, some particular state coming out, but it doesn't really deal with how quickly those changes occur or the specifics of how those changes take place. Where did that additional enthalpy come from? Where did that additional temperature rise occur? How long did it take the fluid to come to that state? And so that's where heat exchange comes in. Right? If thermo allows you to figure out, how much power is being generated by some turbine or something in a system, heat transfer is what gives you the ability to design that turbine so that it is capable of generating that power. And so this is a necessary discipline for everything from heat exchangers, you'll see in big boilers and hot water systems, to the radiators and cooling systems on electronics, to automotive, to understanding the way that heat shielding and insulation works. So early on, we'll start talking about resistance networks, which we see anytime we walk into a hardware store as R values, right? And being able to understand how you use that R value to figure out how insulation in a home affects, right, heat dissipation, all the way up to how that translates to heat shielding on reentry capsules for aircraft or for spacecraft, to radiation and how we can even have things like, crop failures due to radiation frost, as it's called, where crops can freeze in ambient temperatures that are above freezing, right? Because they are radiating all their energy to space. So widespread. Heat transfer has its fingerprints all over engineering. And this is one of the reasons that it's such a cool topic. All right. I'm going to jump over to my note page here. Right, state our objectives for the next, 20 or so minutes that we've got. We've already reviewed the course structure, so I'll leave that out. In the time we have left, we want to actually get around to defining what heat transfer is and what it isn't. And we want to be able to describe the relationship between heat transfer and, some of the more familiar thermodynamic concepts or quantities. All right, so start by asking the question, what is heat transfer? Well, we've talked about what it applies to, why it's important, but How do we actually define it? And so, everyone in this room has an intuitive sense of the mechanisms of heat transfer. Right? Everyone has used it, whether that is, you touch a hot cooking dish, right, or a pan off the stove, and you get burned because the conduction of thermal energy between the pan and your hand, right? How blowing on your burned fingers offers some relief because of the convective cooling, to putting on oven mitts, right, providing some insulation or R value so that you don't, get burned again, to how heat radiated from the burner and the pan before you touch it might alert you to the fact that it is hot and there to cause pain. So, these are things that we do without, a second nature, and without really thinking about them. But just in that little example of the, cooking accident, we've covered kind of all of the mechanisms of heat transfer. So what's interesting, though, is that heat transfer, the name itself, is a little bit of a misnomer. So we often think, about the idea that heat is itself thermal energy. But in reality, heat is the mechanism of energy transfer. So the notion of heat as being a thing, as being a quantity, a noun instead of a verb, comes from like old, science, where this thing called caloric theory that's from the 19th century, where scientists thought that thermal energy, they thought that heat was something that could be accumulated in an object due to this invisible, massless fluid that they called a caloric. This is obviously not the case, right? But this misses out, right, on a lot of the real behaviors of thermal energy. So what they were thinking of was approaching the idea of stored thermal energy. But they called it this caloric, and we've sort of morphed that into heat. So we could say that heat is the mechanism of energy transfer, specifically the transfer of internal stored energy. So there are still some ghosts of that old caloric theory in play today. We still say, we would add heat to a pot of water to boil it, or this room has a lot of heat, right? This thing maybe something that's been heated up in a furnace has a lot of residual heat. These are all basically holdovers from this idea that heat is a thing that you can store inside of an object. So we're going to try to kind of gradually move towards the correct usage, where we talk about heat as a movement of thermal energy from one thing to another. So heat transfer is a little bit redundant, but we're not going to get to, not going to be sticklers about it, because, language changes, and it doesn't hurt anybody really to speak about heat as being a form of energy either. So the other thing that we want to discuss, is the relationship to thermodynamics. And this is where we're going to have sort of a meeting of two of our previous disciplines already. So because heat transfer is grounded in thermo, let's review sort of the the 4 laws, right? We're only going to be really drawing on 2 of these significantly, but we're going to write them all down. So there's what we would call the 0th law, which is really quite obvious. It says, if a body at temperature TA is in thermal equilibrium with body B, such that, right, temperature A is equal to temperature B, and B is in equilibrium with C, such as TB is equal to TC, then A and C, right, are also in equilibrium. A very easy logical extension. TA is equal to TC. All right, now we're getting into the stuff that's going to be a little bit more applicable. So, the first law of thermo. And anyone recall what the first law of thermo actually states? There's a bunch of different versions of it, so there's lots of opportunities to get this right. Any takers? Yeah.
Like hot temperatures go to cold temperatures.
Ooh, close. That is the second law, right? So you're just off by 1, indexing error, right? So first law has to do with basically, yes. It's the first law is conservation of energy, right? The energy is conserved in a system. Energy of a closed system fix my handwriting there is conserved. And so in mathematical form, what this basically means is that the change in a total energy that is stored within a system has to be equal to Q minus W. We'll delve into this a little bit more shortly. We just heard the second law, which has a couple of different statements, but the easiest one to really interpret is that heat transfer cannot occur spontaneously from a region of cold, right, to a region of warm temperature. So this is basically what you were just saying, is that thermal energy has to flow from hot to cold. It cannot go the opposite direction on its own, right? There are plenty of things like air conditioning systems and such that do cause thermal energy transfer from regions that are colder to regions that are hotter, right? It's how refrigerators work, but they don't do it on their own. They have a lot of mechanical energy that's being shunted around in order to make that possible. Okay, and then the third law, which, again, we're getting kind of into the more esoteric here, is that a body, specifically a body that has a crystalline structure, at 0 absolute temperature has 0 entropy. Okay. So we've got these written down. To some degree, we're going to be drawing on all of these, but it is laws 1 and 2 that we're going to be using most heavily in this class. Okay. What I want to do now is take a closer look, or a little bit more of a closer look at the first law, specifically this word system, or this closed system. Oh, I have system written twice. Scratch that one. And the equation that's below it. So last semester in fluids, you guys learned the concept of like control volumes, right? Previous to that, in thermo, you learned about closed systems. You may have talked a little bit about open systems as well. I want to try to sort of combine these notions under one umbrella. Open and closed systems. So when we speak about a closed system, we're referring to a collection of matter with fixed identity. In fluids, we just referred to these as systems, right? A system was a closed system. So this is basically tagging all the molecules that make up some region of a thing and saying those elements of matter are forever part of this system. And so, right, the mass of a system is conserved, the momentum of a system is conserved, the energy of a system is conserved, etc. When we speak about an open system, this is what in fluids we called a control volume. And so this is a region of space through which matter flows, if it wants to, right? If it's the type of matter that wants to flow. So for both, right? For both open and closed systems, there we go. Let's tag these, right? Both open and closed systems. Right? The first law of thermo applies. Which we're going to state in this case as being the total change of energy, okay, that is stored in that system is equal to the net change of energy that is entering the system, total, minus the net energy that is leaving the system. Okay. The major difference between open and closed systems is what goes into this E in and E out. There we go. So for a closed system, we really only have the mechanisms, right? That are, right, the heat transfer in and out, and work, mechanical work in and out, right? In other words, energy can cross the boundary of the system, but it only does so by exerting some mechanical energy on altering the contents or allowing some sort of heat transfer to add or remove thermal energy. So, heat in or out, and work in or out. For open systems, again, these are not fixed collections of matter. These are boundaries in space, okay, regions of space. We have the same stuff, right? We can get heat transfer out and in. But we also have the mechanism of advection. So heat in and out remain. Work in and out remain. But we add in fluid flow, or the ability of mass to enter and leave. And the reason this comes into play, right, is that just like we saw in fluids, matter that is entering our control volume, okay, our open system, can have its own stored energy, right? If you have cold flow entering a region of space, getting heated up by Qn and then leaving at a higher temperature, think like an air handler in a home furnace, then you have basically a net loss of energy through some of that energy being carried across the boundaries of our control volume by the moving matter. You still have heat transfer in, maybe you still have some mechanical work being done as well, but that's something that cannot occur when you have a closed system. So I wanted to differentiate these because we need to understand that both types of system, however we carve it up, can experience work and heat transfer, but only open systems can have flow moving in and out and carrying energy across the boundaries with them, or with it. Now, I've also mentioned, right, this idea of total energy, or I've sort of subscripted. Right? I have subscripted stuff as E-TOT. So what do I mean by E-total? Okay. This is what is referred to, right, as the total energy, and is composed of basically a bunch of different pieces. So this is made up of internal energy, and mechanical energy. So for internal energy, we're just going to call this U, and mechanical energy, we will call ME. Internal energy, this is usually what we think about as what changes when you heat something up, for example, as it's stored internal energy. This comes in a couple of flavors as well. First, we have our thermal energy. And then we've got, right, a whole mess of other types of energy, right? Usually you're going to discuss these in physics or chemistry classes because this includes things like stored chemical energy, nuclear energy, and those are not really what we deal with so much in heat transfer. So we're going to go ahead and just tag these as being other. Right, which includes things like nuclear, chemical, etc. Thermal energy is also divided into two sections, right? There's what we call sensible, and so the easiest way to remember this is basically if it is a change in energy that you could measure using a thermometer, then, right, used to sense it, then it would be considered sensible energy. You take a pot of water and you heat it up, you have added sensible energy. However, if you cause that water to boil, some of that energy goes to latent energy. Actually, we'll just tag this as U sub LAT. Right. And then under mechanical energy, we'll keep this fairly simple. We basically have our kinetic and our potential. Okay, so our total energy, let's tag this as number 1. And then if we grab our thermal and our mechanical, okay, we'll tag this as number 2. We've only got we are out of time. So when we come back on Friday,